In this, we study how to find the Laplace transform using the second shifting property. Sometimes we also call the second shifting property as second translation property. So in short, we call SSP, second shifting property. The second shifting property says the Laplace transform of a function which is f t minus a times ut minus a. What is the u? U means the unit function, what we call the unit function. Unit function. So when you multiply those two, then the Laplace transform is simply e to the minus as times fs. So you can see this minus a again appear here. So all three times you have minus a and minus a. And then you transform by the original Laplace transform of the original function fs. That's what it says, multiplied by fs. So what is this unit function? So unit function means it is going to be 0 until a. Right after a, you can see it is 1. So it's going to be 1. So these are normally what we call the switching functions. We're going to switch on the function after a. So if you write this as these are the piecewise functions. So if you write this as a piecewise function, you can write this one as u t minus a equals to 1 if you can say if t is greater than or equal to a, 0 otherwise. So you can say it like that. So it is a piecewise function. It's going to be switch on after a, otherwise it is 1. So that means you're going to pick up a part of a graph or part of a function after that, after a. So that's the idea. So, so this is one way to say it. And then also there's another second version. This is second version. So as a second version is this one. So here what happens, sometimes your function is not given in the right form, because to use the previous form it has to be t minus a, t minus a. This should match. But sometimes that doesn't happen. You just get a regular function like ft without t minus a. So in that case what happens is, you can see there's a slight different version. The ft plus a goes to the other side. Is t plus a goes to the other side. So how to remember this one? So there's an easy way to remember this one. If you write on the negative side, let's say this is 0. On the negative side, you write t minus a. If you write on the positive side, the other side, you write t plus a. So that's like easy way to remember this one. So if on the negative side, you write t minus a. On the positive side, you write t plus a. Okay. So, so this is what we normally call the second shifting theorem or second shifting property, or SSP. So now let's see how we can use this idea in a few problems. So find the Laplace transform of the following functions. So let's start with the first one. So let's look at this one. So Laplace transform t minus 2 ut minus 2. And when you look at this problem, you can see it is in the right format. T minus 2, t minus 2. That means if you use the formula says it is equals to e to the minus 2s, is the same number again, minus 2. And then the Laplace transform of the original function. In this case, what is the original function? T. T is the original function. So we write this one as ft. And then we know that the Laplace transform of t by the table method, we know that it is simply 1 over s squared. So we're going to plug in that here. So if you plug in that, so you can write it like this, e to the minus 2s, and then 1 over s squared, and then finally we multiply them and write it like this, squared. So later, like once you get enough practice, you can directly write this answer just doing a lot of calculation, like mental calculations. So let's look at the next one. So the next one says, find the Laplace transform 3 times t plus 1 squared ut plus 1. So when you look at this problem, you still see that the t plus 1 term again appears here. That means it's in the right format. And then what is a? Because since you need a negative sign, here a is actually negative 1. Because the negative become positive. That's why you have positive sign. So a is negative 1. So that means if you use the formula, so what you can do is, you can write this one as e to the, so in this case a is negative 1, and with the negative sign the formula is going to be positive 1. So it is positive 1 s. So the easy way to remember this one is, you can see this number, the same number going to appear here. So that's the easy way to remember that. And then what we do, we find the Laplace transform of the original function, which is 3t squared. And then let's recall some of the formulas, and we know that the Laplace transform of a polynomial like t to the n term, what we call monomial, so which is simply factorial n divided by Sn plus 1. And because of that, you can see t to the squared actually going to be factorial 2, which is 2 divided by S2 plus 1. So because of that, now you can write the answer. We can pull 3 out, and then we have e to the s, and then write the transform here, so which is going to be 2 factorial over s to the 2 plus 1. And if you simplify, we know factorial 2 is 2 times 1, 2 times 1. So that means finally you can write this one as 6 e to the s over s3. So this valid for is positive, s positive. Good. Okay, let's do the next one. As the next one, we have a trigonometric one. So we have u t plus 2 sine t plus 2. So same formula. Here again a equal negative 2. So that means if we plug in to the formulas, you can see that what you're going to do here is e to the 2s, and the Laplace transform of the original function. In this case, the original function is sine t. That's the original function. So it is sine t. And then from table, we know that the sine t has this format. So it is e to the 2s. Sine t is going to be a squared. Omega in this case is 1, so 1 squared. Omega means the number in front of t, so which is 1, the coefficient, and then 1 here. So if you finally write this one all together, you can write this one as e to the 2s divided by s squared plus 1. So that's the transform of that. So now let's try to look at a slightly different problem. So let's call it D. So how about this one? Suppose we have this problem. So here you can see that you have a cosine t. Cosine t, and you don't see that special t minus pi over 2 term. So if you get a problem like that, you can do this in two different ways. The one way is to use the second version of the second shifting theorem, second shifting property. So what the second version says that, so it says we still write e to the minus pi over 2s. So we have that, but here is a Laplace transform of not the original function. You have to shift the original function, is a cosine, shift the original function by the opposite sign. So it is t plus pi over 2. So that's what happened. So that's the second version of the shifting theorem says. You need to have opposite sign here. So now after you get to that, now what we can do, we can use the trigonometric identities for that. So first you try to simplify this part first. You have to simplify this first. So you do that first. So that means it is e to the minus pi over 2s. So and then from the trigonometric identity, you know this property. So you can write this one. So we know that the cosine t plus pi over 2 is equals to cosine t cosine pi over 2 minus the opposite sign sine t sine pi over 2. But here you know that the cosine pi over 2 is 0, so this term is gone, and the sine pi over 2 is 1. So that means this whole thing simplifies to negative sine t. So that's what happened. So because of that, now what we can do is, you can write this one as, so you can pull the negative sign out. So this e to the negative pi over 2 s, and write the transform of sine, so which is s squared plus 1, 1. And then if you combine all of them, you can write this one as negative e to the negative pi over 2s divided by s squared plus 1. So this is like one way to do it. The other way to do is you can directly use the trigonometric identities at the beginning. So let's look at that approach. So this time what we're gonna do, we're gonna see whether you can rewrite the first one using t minus pi over 2 term. For that, what we can do, remember the complementary function property. So it's a complementary function property for sine and cosine. So it reads that, so we have cosine t equals sine pi over 2 minus t, or sine t equal cosine pi over 2 minus t. So we can use the first one. So if you use the first one, you can rewrite this one like this. So you can say this is sine, and then pi over 2 minus t, and then u t minus pi over 2. So we have this. But still, we have problem. You can see this is not the right direction, right format. So what we do, we know that sine is an odd function, so we can switch the order. But when you switch the order, the negative sign comes out, we can write the negative sign outside. So we can write this one as the Laplace transform of sine. Now you switch the order, so you can write this one as t minus pi over 2 and u t minus pi over 2. T minus pi over 2. But now you can see that that's in the right format. So since the right format, now we can use the shifting property, first version of the shifting properties, which is negative, and it is e to the minus the same term minus pi over 2, so it's minus pi over 2s, and then the Laplace transform of the original function, which is sine t, not the transform version, so which is s squared plus 1 and 1. So if you combine together, you get e to the minus pi over 2s divided by s squared plus 1. So that's how you get, and you can see both answers are the same. So it should be, but you can do it either way. You can use the trigonometric identity inside or outside. Okay, so let's look at the next one. Let's say we have e to the 2t u t minus 3. So again, you can see that there's a t minus 3 terms. So here I'm going to teach you like a different trick here. So what we're going to do, so I'm going to leave some space. Let's try to recreate the term we need. So we need the t minus 3 term. So let's recreate that. So that means it is e. Instead of 2, we write t minus 3, the way we want it. And then we have u, t minus 3. So we have that. And then you can see when you do that, this is not exactly what we have, but you can see it's gonna introduce this extra term, e to the negative 6. We have 2 times 3, which is negative 6, so e to the negative 6. Just to cancel that, we can write e to the 6 outside. So that's what it is. That's the trick. Once you do that, now you can see this is in the right format now. So we can directly use the second shifting property. So if you do that, now it is e to the 6. So we have, and then we're going to get e to the term is negative 3. So that means it is negative 3s, and then the Laplace transform of the original function. So in this case, the original function is e to the 2t, e to the 2t. That's the original function. Because we just forgot about the transform part and pick this part as the original function. And then from the table method, and you can see that, so that's the a. So we just need to subtract that from the denominator. So that means we can write the answer like this. So you can say that this is e to the 6, and then actually you can combine these two. So you can write e to the negative 6 negative 3s, and then here you're going to get 1 over s minus 2. So if you put all them together, it is e to the 6 minus 3s divided by s minus 2. So that's one way to do it. So we directly use the second shifting property. So we use the second shifting property. So let's also use the second version of the second shifting property. So if you use the second version, what we're going to do is, so this is like a method 2. So you can see method 2. So you can write this one as Laplace transform of e to the 2t u t minus 3, and then you can write this one as using the second version. So it's still the second shifting property, but the second version. So which says that we still write e to the in this case negative 3s. So we write that, and then here it is going to be the Laplace transform of e to, but not t, it is t plus 3. So opposite sign, plus 3 is a minus, so with a plus. Now we try to simplify this one as before, and you can see, so what we're going to get is, and we know that there's no formula for the transformed version, so what we can do, we like a similar algebra like last time. So what we can do is, we can write this one as e to the 6 times e to the 2t. So you can write it like that, and e to the 6 you can pull out, and then e to the negative 3s, and then the transform of the e to the 2t, and you can see this is very similar to the previous one, so that means you get the same answer in this case also. So just do a little bit of different algebra here, that's what happened. So you get e to the 6 minus 3s over s minus 2. And also there's another version, you can also use the first shifting property for this one. So you can also use the first shifting property. So let's use that and see how the answer, you're going to get the answer for that. So let's do that now, method 3. So what's the first shifting property says? So you can remember the first shifting property in either way. So what it says that, so easier to remember this one, have the opposite sign inside. So it's a negative become positive, or positive become negative, just the opposite sign. So because of that, now we can write the answer like this. So we have e to the 2t ut minus 3. So what we're going to do, you transform the original function and then shift by 2. So that means we know that we know this property of the unit function ut minus a has the Laplace transform of e to the minus as divided by s. So that's the formula. So because of that, you can write this one as e to the minus 3s divided by s, but you have to transform s to s. You can see because we have a 2 here, so it's s minus 2, opposite sign. So that means if you do that, you can see it is e to the minus 3, replace s with s minus 2, and also the bottom replace s with s minus 2, and you can see it simplifies to the same one as before. So you get e 6 minus 3s divided by s minus 2. So you can get the answer in 3 different ways as we did here. So anything works. Okay, so let's look at a last problem, but this time we can look at it like a slightly different problem. How about this? So we have t squared u to the t plus 1, and again they are not in the right form. So you know that you can do this using the second version of the second shifting property, second version, you can directly do that. But I'm going to teach you a different trick here. So what we're trying to do, we try to rewrite the t squared term using t plus 1. So that's the idea. So let's see how we can do that. So let's look at t squared. So you can write t squared. So this is a trick, t squared. And then we can write inside t plus 1 and minus 1, because that's still t. And then you're going to bracket the first one and leave the other one, and then we're going to square this. So that's the idea. So you try to recreate the term that you need, and then use the identity, and we know that a minus b squared is equals to a squared minus twice ab plus b squared. So we can use that here. So if you use that, what are you going to get? You can see that it is going to be t plus 1 squared minus 2 times t plus 1 and then plus 1. That's what you get. So if you go back to the original problem, now what we can do, we're going to replace t squared by this. We're going to replace t squared by this one. So if you do that, and you can see this is t plus 1 squared minus 2 times t plus 1 plus 1, and then whole thing multiplied with u t plus 1. That's what you get. So now what we can do, we're going to rewrite the whole expression again. So what we can do, because of linearity, we can break it down to 3 parts. So we can break it down to 3 different terms. So we can write this one as Laplace transform of t plus 1 squared and then u t plus 1. So we can, and then as the first term minus, and you can pull 2 out, and then you can write this one as t plus 1 u t plus 1, and then you can write finally the last term, which is plus, which is u t plus 1. Now we can use the second shifting property for term by term. So that means if you use for the first one, you can see they match now. So they match, all of them match. So that means we can write it. So that means it is going to be e to the s times t plus 1. T plus 1 means original function is t squared. So that means it is going to be 2 factorial over s 2 plus 1. That's the first one. Go to the next one, which again e to the s with the 2, and then here it is term is t, so that means it's going to be 1 over s squared, and then last one is again e to the s. Here the function is in front of the function is 1. You see 1 here, so 1 means 1 over s. Okay, so you can write the final answer like this. So you can write the final answer like this. So you may wonder why we want to do that. Actually, you will see that these kind of functions are really useful when you try to solve a certain type of differential equation. For example, this one. So it will be useful when you try to solve something like this. So let's say y triple prime plus 2y prime equal ft, where ft is ft equal t squared if t is greater than or equal 5 and 0 otherwise. So that means if you look at the graph going to look like this. So you can see it is only, well, so we have this t squared function, but it's not all, it's only valid after 5. So if it is 5, you actually start seeing the graph. So that's the situation. After 5, you start seeing this. That's ft function. So if you have something like this one, actually you can see, you can rewrite this function as ft, and then, so in this case ft means as t squared, so let's write t squared. So you can write as t squared u t minus 5, switch on after 5. And you can see, so it's a similar situation, and we figure something like that. So you have to find the Laplace transform, and then we do the same thing like as we did before. So you can either use the second version of the shifting theorem, or you can rewrite like using polynomial. You can write it like that. So you can use either method. And it is also very important if you have a piecewise function like this. So let's look at this one as the last one. So it is 0 before 2. So it is 0 before 2. So if t less than 2, it is 0. And then it is t squared between 2 and 3 without 3. And then 0 again. So let's look at the situation like that. So if you look at the graph, it's a very similar idea. So that means it is not the whole t squared graph. It's only going to pick up the graph between 2 and 3, and then 0 again. That's a 2 and that's a 3. So that's the idea. So that's what happened in this case. So that's the graph. So the question is how to get the Laplace transform of this, and these are also really important in practical situations. So let's say like you're going to switch on something between a small period and then switch off again. It's only valid in this region, just this part. Okay. So that means we can write this one as like this. So you can say, so it's a t squared, and then you're going to switch on this one at 2. So that you can do by multiplying by t minus 2. So you can switch on at 2. This is on. And then what you're going to do at 3, you have to switch off. How to switch off? You're going to switch on another function and you subtract that. So this you multiply this one by ut minus 3. That's what you do. Because right after you do that, it's going to switch off the function at 3 because both are 1. 1 so it's going to be the difference between 0. So that is the idea. Now after you get to this one, and then you can distribute this one as two different functions, because you can write this one as t squared. You can write this one as u to the t minus 3, t minus 2, and then t squared u to the t minus 3. So now we can do the same thing again as before, using either way, first shifting property or the second shifting property, and you can get the answer like this. So if you use the second, this is coming from the linearity, you can break it down, and then if you use the second shifting property version 2, you can write this like this. So you can see the first one has the opposite sign, so minus become plus, and same thing, minus become plus. Now what we're going to do, we're going to distribute this as a polynomial, so you can write it this like this. Now if you do term by term inside and then collect them, you get the final answer like this. So this is the final answer you get, and you can combine them, but it doesn't make any big difference, so we can leave it like that. So these are the several different type of functions that you can handle using the second shifting property. So I hope this helps. So now you can try these problems and see whether you can get the answers. So try these practice problems now. Now try these problems as practice problems and see whether you can comment below if you know the answer. So there are some interesting ones here. So the first one is like kind of straightforward, and here you might have to use some identities or second version of the shifting property, and think about how to handle this one. You see there are two different numbers here. You need some manipulations there, and for this one is match, so that's an easy one. But here you might have to distribute. See, you have this, and but also you have to use the either second version of the property, or you have to rewrite all the terms within t minus 3. The last one is interesting. That's a piecewise function, so you have to rewrite this using switches first, and then you transform it. Okay, so these are the problems that you can try.